Hello and welcome to today's e-seminar. Today's learning goals are to become more familiar with water and steam hammer and to see how AutoPIPE uses Korteweg's and Joukowski's equation to analyze for this effect. We will also see how a similar approach can be used to represent the effects of slug flow. First, let us look at the different types of unsteady flow. In normal operating conditions, flows are considered to be steady, where the velocity and other flow quantities are unchanging over a period of time. Normal algebraic methods can be used to predict the behavior of such systems. When the flow becomes unsteady, the flow conditions become considerably more difficult and require complex computer simulations to predict their behavior. Elastic forces are produced in a pipe when these flow conditions change. In general, the speed at which the change occurs dictate the severity of the elastic forces that exist, and where they occur rapidly, as in fast-acting valves, then they should be considered in the piping analysis, as they can lead to structural failure of pipes and/or supports. Even in the human body, a water hammer pulse can exist due to backflow through the aorta, causing a sudden drop in pressure. Much of the same theory applies, and equations developed for pipelines are also used in hemodynamic studies. To illustrate the potential magnitude of such forces, let's consider a perfectly rigid pipe with entirely incompressible fluid and an instantaneous valve closure. According to Newton's second law, bringing the contents of the pipe to rest instantaneously would result in an infinite force. Thankfully, fluids are not completely incompressible, especially gases, nor pipes rigid or valve closures instantaneous. However, these dynamic forces can cause significant problems, as seen in the picture that shows the failure of flexible joints due to steam hammer, and in this YouTube footage, where you will hear and see the effects of water hammer. So how can AutoPIPE help us consider these effects? AutoPIPE can consider the effects of valve closure and opening, relief valve lift, and slug flow. By using force-time history dynamic analysis of the transient condition, the large reactions at supports and stresses in pipes can be determined so that the system can be adequately designed to withstand them. So let us consider the case of valve closure or opening. During normal steady-state operation, the system remains in equilibrium with a constant pressure or head and flow along the pipe. The pressure head in the pipe is represented by the blue line, and the movements of the contents can be represented by the train trucks that are all moving along at the same velocity. If we consider the valve closes very rapidly, then there is a change in kinetic energy due to the moving fluid being brought to rest at the valve. This energy is converted into potential energy in the form of a large pressure spike or increased head at the valve. In the train, the truck at the center is stopped, but on either side they continue to move at the same speed, as does the fluid in the pipe, towards the valve upstream and away from the valve downstream, as only the fluid at the valve is stationary. Further upstream, the contents continue to move towards the closed valve, and the pressure spike or wave moves back along the pipe as the fluid comes to rest. The train shows this happening as each truck closes up in turn to the stopped truck on the upstream side and moves away on the downstream side. The wave will continue to travel back along the pipe until it reaches a closed end, a reservoir, or something that stops its propagation. On the downstream side of the valve, a similar but opposite effect happens. The pressure wave is negative as the contents continue to move away from the valve. The train trucks show this as they move further apart in turn. When the positive and the negative wave reaches the ends, it then reflects and returns back towards the valve, creating a positive wave downstream and a negative wave upstream. In the absence of friction and damping, this will continue indefinitely. In this YouTube video, we can see the effect of the reflecting wave in this stormwater system on a Calgary highway. The surge arrives at the manhole and lifts it up onto the highway. A car crashes into the manhole cover. After some time, the surge recedes and then is travelling back towards the closed valve or reservoir. It will then return back to the manhole and nearly washes away the man that was driving the car. It is a change in kinetic energy due to a change of velocity as the fluid comes to rest that produces the pressure surge at the valve. A simple relationship that links change of velocity to change of pressure is known as the Tsiolkovsky equation, where the change in pressure is equal to the fluid density times the speed of sound in the fluid times the change in fluid velocity. In 1878, Korteweg mathematically described the relationship of the speed of sound of a fluid in a cylindrical pipe. His work was stimulated by the experimental work done earlier by Mons, where K is the bulk modulus of the contained fluid, D the diameter of the pipe, small e the wall thickness, and capital E the modulus of elasticity of the pipe material. You will see that the speed of sound will be affected by the compressibility of the contents as well as the flexibility of the pipe wall. So in thin wall pipes, the speed will be slower than in more rigid pipes. Although commonly known as water hammer, the same effect can be witnessed in gas and steam lines. Because the bulk modulus and density are lower, the speed of sound is slower in gas or steam systems, typically for air at sea level around 4.3 times slower than in water. If we ignore the change in pressure due to the change in height, the pipe system can be considered to have the same internal pressure throughout its length, illustrated by the blue circles. In AutoPIPE, the fluid transient module calculates the pressure rise at the valve using the Tsiolkovsky's equation, and the speed of sound of the wave using Korteweg's equation. Knowing the geometry of the piping system, the program can automatically calculate the time histories for each part of the system as the wave travels through it. So the moment the valve closes, the pressure at the valve increases, and a force given by pressure times cross-sectional area is produced. The actual force exists due to the imbalance in pressure from one end to the other. The force remains for the duration the wave takes to travel to the next change of direction, where the pressure at both ends is then equalized. The force then disappears and appears in the next section, and so on. Let us see this again. The valve closes and the pressure increases, producing a force in leg 1. Pressure increases at the bend and the force appears in leg 2 and reduces in leg 1, and so on into leg 3. The closure time for a valve isn't instantaneous, and it takes some time to close. The graph shows a typical valve closure which produces two shock waves, a positive wave upstream and a negative wave downstream. The magnitude of the force in each of the pipe legs is dependent upon the time taken for the wave to travel between the bends, and unless these bends are very far apart, as with cross-country pipelines, or the valve closure is very rapid, the maximum force produced from 100% of Tsiolkovsky's pressure rise will never be reached, as there is insufficient time to build it up. To illustrate this, let's assume our valve has a slow closure time of 1 second, and the time taken for the pressure wave to travel the distance L1 is 0.4 seconds. The pressure builds up as the valve closes, but before it can reach maximum pressure, the wave has travelled down the pipe and reached the first bend. The pressure there begins to rise, balancing out the pressure at the valve. The force in the pipe is a resultant of the increase in differential pressure from one end to the other, and due to the pressure increasing at both ends of leg 1, the differential pressure is much less than the maximum pressure predicted by Tsiolkovsky, so the maximum force will not exist in this leg. This will also happen in each of the following legs as the wave moves through them, until it reaches the end. The longer the distance between the bends, the more the differential pressure can build, and the bigger the resultant force will be. The total time the wave takes to travel to the end and back is dependent on the total length of the system and the speed of sound. The AutoPIPE module doesn't calculate the effect of reflected waves, or include friction losses. However, it does calculate the reflection time, which is equal to 2 times the total length over the speed of sound, 2L over C. If the wave returns to the valve before the valve is fully closed, for example in a relatively short system, then the maximum pressure rise calculated by Tsiolkovsky for the complete valve closure cannot be achieved, as the fluid flow will continue through the partially closed valve. In this case, the approach is conservative, and AutoPIPE will report a warning to that effect. In most cases, the first wave is usually the one with the most energy, and this will have the most structural effect. The reflecting waves can be less onerous due to losses. Let us consider this simple pump suction and discharge system to illustrate the use of AutoPIPE's fluid transient module. The two parts of the geometry are separate, as the pump has not been modelled. At the end of the discharge line there is a valve, which will close rapidly to create the fluid transient. Since AutoPIPE uses a modal solution for dynamic problems, we must first ensure that we have sufficient mass points to define all the mode shapes in the model. In the Edit Model options under Tools, we have the ability to define the amount of mass points between the model nodes. By using A for Auto, we can let the program calculate the number of mass points required to produce all the mode shapes up to the cutoff frequency we specify. The calculation uses half the length from standard formulae for natural frequencies in simply supported beams. We can now set up the modal analysis, and we will calculate all natural frequencies up to 200 Hz. Note, for dynamic events produced by axial loads, a high cutoff value should be used. This is because axial natural frequencies can be higher than lateral frequencies where we have axial restraints. Animating the mode shapes for this modal analysis, we see the shape and also the frequency of the first mode of 2.6 Hz that we will use later. The frequency report will list the natural frequencies calculated and reports the participation factors and captured modal mass for each frequency. It also reports the total mass participation in the full modal analysis, and here we can see it's 83% of the total mass of the whole system. We can now define the transient event using the fluid transient module under Load. Here we can select a standard fluid from the library or define the properties of non-standard fluid. The start time and rise time of the closing valve is defined, and the section of pipework that the transient applies to, starting at the valve at C12, the source of the transient, up to the pump discharge at C00. The flow is in the opposite direction to the defined section and is therefore specified negative. You will see already that the module has calculated the Tsiolkovsky pressure rise of 228.7 psi, 15.8 bar, and the speed of sound from Courtois' equation at nearly 50,000 inches per second, or 4,572 kilometers an hour, or 2,840 miles an hour. The maximum pressure rise would give rise to a force of 25,650 pounds, or 11,660 kilograms. Accepting the input initiates the transient calculation for the specified parts of the system that are highlighted in red. The time history locations THL file is produced. In here you can see the node location of the forces, the time history profile TIH file names that describe the time histories, their direction, the maximum force applied, and the time that it will apply. You'll notice that the longer legs have larger forces applied, due to there being more time for them to build up the pressure at one end before it starts to equalize out at the other end. but nothing as high as the maximum force of 25,650 pounds. Total time for the pressure wave to travel the full length of the system and the time taken to travel twice the distance are recorded. A warning is given that the rise time, or in this case closure time, is slower than the 2L/A time, and thus the analysis will be conservative. Note that this module uses A to denote speed of sound and not C. We follow a similar process for the suction side, delaying the transient by the amount equal to the time taken for the wave to travel from the valve to the pump. This results in another time history location file and another group of time history profiles. Here you will notice that the speed of sound and the pressure rise is slightly less in the larger pipe, as is the velocity due to the increase in area. We can now take a look at the time history profiles defined by the TIH files. The profile shows how the force increases as the pressure builds up at one end and then flattens out as the wave reaches the other end. You can save these profiles for use in a report. All the dynamic time history loadings are now complete, and we only have to define the type of analysis we require. We can use the same modal analysis settings as before and move to the time history tab. Here we select the two time history location THL files that describe the transient and select one of the two integration methods, either piecewise exact or Wilson theta method. For the duration we use the L/A time plus the period of the first motor as a minimum time, and in this case that would be a time greater than 0.42 seconds. Inclusion of the ZPA, the zero period acceleration, will provide a static check to ensure no significant axial modes were missed in the analysis. The static and dynamic analysis is performed and the results created. AutoPIPE automatically combines load cases into code-compliant combinations depending on the selected design code. You will see here that the time history case is combined with the sustain case in line with the requirements for occasional loads. Also, the non-code combinations are available for us to define operating loads on equipment and supports by combining the operating load cases. By displaying the interactive scan of the stress results, we can see that it is an occasional stress that produces a largest stress ratio of 1.53, indicating an overstress. We can review the displacements caused by the fluid transient by selecting the time history case. You will notice that the maximum displacement occurs at the end of the long pipe, where the force was the highest. Stopping the animation, we can read the value of 1.17 inches or 30 millimeters of X displacement at that point. There is no axial restraint on this pipe, so there is a potential that the force could cause failure of the pump discharge connection. The tricolour deflection lines shown at all points help visualize the direction of the displacement by relating them to the XYZ axis. To help the user better understand the time history results, we have a post-processor that displays all the results by way of a time history graph. So looking at the bend at C10 where the displacement is the greatest, we can see the deflection profile of this point with respect to time, and the same 1.17 inch maximum displacement in the X direction. The displacements in the other two directions, as well as the force time history at that point, is also available if required, and graphs can be saved for use in the stress report. Using the interactive scan of the stress results, we see again the coloured plot that shows the maximum stress ratio of all points and shows that the occasional stress case of sustain plus time history is the peak stress combination, showing an overstress of 53%. Mainly due to the lack of axial support on that line causing large moments in the connected sections. The addition of a simple line stop in this line provides a solution to this high stress, now showing a maximum ratio of only 77% of the allowable. The Eurocode has some advice on considering dynamic and static loads. A simplified static approach ignores the interaction of waves and the dynamic response of the system, and is usually conservative. The dynamic approach can be considered more accurate, but is highly sensitive to the characteristic of the valve closure, supports, and fluid behavior. It will also be sensitive to missing modes if a modal analysis solution is used, so the designer should ensure that all the significant modes have been included and be comfortable with the approach. To illustrate the static conservatism in a simplified static approach, we can see here that if we apply the maximum force resulting from Tsiolkovsky's pressure rise, we get a huge stress. This is mainly due to the action of the wave around the system not being considered and the effect that this has on equalizing the differential pressure. If we take account of the wave movement and apply the forces calculated by AutoPIPE's fluid transient module statically with a conservative dynamic load factor DLF of 2, the maximum stress ratio is 2.05. Compared with the dynamic approach value of 1.53 before the line stop was added, this indicates the conservatism of the simplified static approach. By applying the same forces without a DLF, we see the ratio of 1.14, which is less than the dynamic value. This is expected behavior as the dynamic effect will amplify these applied loads, and this is the purpose of the dynamic load factor, which is usually between 1 and 2. If we consider a more complex analysis, like this steam system, the fluid transients due to rapid valve closure can be performed by running a number of AutoPIPE fluid transients adjusted for flow and timing as the wave travels around the system. The profiles produced can be then included into a number of time history location files before being further combined in the time history analysis sets. Here you can see the stress and deflection results from this analysis. In this example, we want to carry out a more complex fluid transient analysis, and for this we can use a third-party program to produce the time history profiles. The time history profiles coming from these kinds of programs will contain many more points than those produced by AutoPIPE, as they can pick up effects that AutoPIPE cannot, like phase changes, attenuation, cavitation and reflected wave effects. We need to import the data into AutoPIPE and assign it to a location. This can be achieved by copying the columns and pasting them directly into the AutoPIPE profile dialog if the data is not already in the form that AutoPIPE can read directly. You will notice that the two profiles are the same. In the early 80s, Goodlin investigated steam hammer in power generation plants. Whilst this flow condition was considered in nuclear plants, it was less common to do so in non-nuclear plants. Due to the large temperatures involved and the long lengths of main steam and reheat lines, large displacements were witnessed during turbine trips of the order of 18 inches or 450 millimeters, due to transients caused by rapid closure of steam valves. He proposed a simplified approach to calculate the forces and displacements in the piping system that provides good correlation with the method adopted by AutoPIPE. We can see here a similar pressure rise of 154 psi is obtained, leading to a maximum force of 6,216 pounds and the 61-foot vertical line. The results of the analysis show that the occasional stress in the system is within acceptable limits. The maximum displacements in the horizontal line correlates with Goodlin's approach. Goodlin concludes that although sophisticated analysis is possible, he questions the need for it, when a simplified approach like the one adopted by AutoPIPE gives reasonable conservative results. Another flow condition that produces similar effects to the water hammer effect is slug flow. Here we have two different phases of fluid that can occur for a number of different reasons, including condensate collection, system startups, cavitation, flashing, etc., and can be very damaging to piping systems. When they move around the system, they create dynamic loadings due to the change of momentum at bends and reducers. Although these slugs are hard to predict and are unstable, AutoPIPE can model these changes of momentum as force time histories. Unlike the water hammer effect, when the force is due to the differential pressure at either end of the pipeline as the pressure wave moves around it, slugs are masses moving inside the pipe that enter and exit the bends, causing a change of momentum. Newton's second law tells us that we need a force to produce a change, and that it will be proportional to the rate of change of momentum. By Newton's third law, we also know that the fluid will exert an equal and opposite force on a solid boundary, producing a change of velocity. We also know that the momentum of a particle is the product of the mass times the speed. In a pipe, the mass flow is given by density ρ times area times velocity. For a 90-degree bend, the velocity changes from v to 0 in a particular direction. So the slug force is therefore ρ times area times velocity squared. As the slug leaves the bend, it now accelerates from 0 to v, thus producing another force 90 degrees to the first. The magnitude of these forces is large. We can see here for a 3-meter slug in a 12-inch pipe, a force of 13.5 kilonewtons, approximately 3,000 pounds, is produced. Force can be represented as two vectors applied to the near and far point of each bend, or it can be represented as a single vector applied to the midpoint of the bends. By calculating the appropriate angle and magnitude, this will require additional calculation for all elbow angles. The slug is moving much slower than the pressure wave in the water hammer case. The speed of the slug and its length, together with the size and length of the bends in radians, determine the shape of the time history profile. It takes a certain time for the front of the slug to completely enter the bend, equal to the radius times the angle in radians divided by the velocity. During this time, the force builds up to the maximum value previously calculated. The front of the slug then travels through the bend where the maximum force continues to apply, until the slug end has travelled through the bend and exited when the force reduces back to 0. While the same force applies to a given pipe size, each bend angle and radius will need a separate calculation to alter the timings and result in a separate profile. The time history profiles for each bend angle and size are defined, as well as the time history locations, with the start times for each profile calculated from the length between the points divided by the slug speed. Remember, this is a modal analysis, and we need to consider the mass point spacing for the same reasons as we did with the water hammer example. Let us consider this simple piping system to illustrate the use of AutoPIPE time history analysis to represent slug flow. The first thing we need to do is to define the time history profiles and create the TIH file for each bend size and angle from under the load menu. We will start with a 90-degree bend, give a name and select the history type. Then define the profile from the calculation of slug force and time history profile timings already done. This profile can be saved and used in a report. To complete the model, we have a 45-degree bend also that I have already defined. The profile is similar in shape, but the entry and exit times are shorter due to the bend angle being less. The time history profiles are now assigned to each bend near and far point using the time history location dialog and the THL file produced. To save time, I have already defined this, and you will see the directions of each of the time history forces and the time delay as the slug moves through the pipe system. Since AutoPIPE will use a modal solution for the dynamic problem, we must ensure we have sufficient mass points to define all the mode shapes in the model, like we did for the water hammer example. Use a high cutoff value to be certain to capture all the high frequency modes. Now set up the dynamic analysis set, including the modal analysis tab. Select the THL file, the integration method, duration time and results required. Checking the results, we see from the interactive scan that the occasional stress is the highest ratio and is showing the system is overstressed. The displacement plot shows the expected displacements during the time history event. Location of the guide on the line A03 to A04 will prevent the large ZY displacement, and we can show that this reduces the stresses to an acceptable level. The time history post-processor can be used to review the forces and displacements in detail and shows that we have a large X displacement at A03. We may want to consider stopping this with a line stop. It also shows that the maximum displacement is near the end of the transient, which could indicate that we need to run it for longer. It is normal process design to avoid the existence of slugs in piping systems in the first instance, but there are some features and operating procedures that can be employed to minimize the effect of them when they cannot be avoided. Here we see an example from industry of slug control during well startups. We are currently working on enhancing the software to provide a view option for the display of time history vectors that will assist in the checking of applied loads, and a slug module similar to the water hammer module that will calculate the magnitude of the applied force and the profile timings based on some information about the slug. Information like area and leg length are extracted automatically from the geometry. So whilst the AutoPIPE approach can be a little conservative in some cases, it does provide realistic results in most flow conditions and can indicate where potential issues may exist in more complex flow conditions. I hope you found this presentation useful, and I thank you for your time.